Hi, this is the last video on graph theory, and this is one more theorem that characterizes what a graph is. So, we have our original definition, which is that a graph is a tree if it's connected and it has no circuits. We also now know that a graph is a tree if it's connected and has exactly n-1 edges. And now today we'll prove that a graph is a tree if and only if there's a unique path, so only one path between any pair of vertices. Okay, so we have two proofs really to do. For the first direction, since a graph is a tree, so if T is a tree, then and UV are vertices, there exists a walk from U to V, because that's the definition of a graph being connected, because T is connected. And what you're showing this week in your homework by exercise 10.1.17, every walk contains a path. Okay, so if we have a walk from U to V, then we have a path from U to V. All right. So if a graph is a tree, then we get a path between every pair of vertices. And I'm going to show now that that path has to be unique. Okay, so now we show that this path must be unique. Well, let's think about this and let's draw a little picture. Let's do a contradiction. So suppose there exist two different paths from U to V. And we'll call them P1 and P2. Both start at U and end at V. So in the beginning, they're the same, and at the end, they're the same. All right, so what I'm going to do now is say, follow both paths until the first vertex, until the last vertex they have in common. Okay, so basically they're both starting at U, they go along together, and then maybe P1 goes this way and P2 goes that way. And we'll call this vertex W. So last vertex W that they have in common. And then the two paths do their thing. Eventually the two paths coincide again because they have to meet up at V. They might meet up before V. So maybe here, they're coming together again. We'll call this one X. So let X be the first vertex where the paths coincide again. Okay, so we know they have to coincide at V, they might coincide before then. And now if you look, And what we have, if we follow P1 from W to X and follow P2 from X back to W. So there are no vertices in common there. So there in particular are no edges in common there. So that's a cycle. Okay, we have a cycle, which is actually a circuit, also a circuit. So it's both. Maybe I'll write circuit because that's what we need for the definition, but it's actually a cycle too. Oh no, what's going on here? So we have a circuit, which is a contradiction because T is a tree. Okay, so that means we've proved the forwards direction, that if I have a tree, then there must be a unique path between any pair of vertices. And for the other direction, well, if I have a unique path between any pair of vertices, clearly my graph is connected because every path is a walk. So if G has a unique path between every pair of vertices, then G is connected. And I claim G can't have any circuits, again, because if I had a circuit, then I would get two different paths. I could go, if I had a circuit, like, then, and I picked two vertices in that circuit, I would have two different paths joining those vertices. Okay, so if G had a circuit, then for any pair of vertices in it, there would be two paths. There'd be two paths between them, okay? Because I could go one way along the circuit or the other way. All right, that's it.